This is Physics 30, Chapter 6, Lesson 2. Today we're looking at types of orbit. Thinking about going into orbit. Imagine launching a succession of rockets upwards at increasing speeds. So your first one is rather slow, your next one goes a little bit faster, third one goes yet faster, fourth one goes even faster, etc. The first few would fall back to Earth, but eventually one would escape the Earth's gravitational pull and would break free when it gets to some breaking point. Now, if we consider that same idea but launching sideways from a mountaintop, if we achieve a speed v such that v squared over r equals gravity, then the projectile would orbit the Earth at the surface, which is what we see in the animation below. How fast is this, you might ask? That velocity would be about 8,000 meters per second, which would be about 8 kilometers per second, which is about 28,800 kilometers per hour, or approximately 18,000 miles per hour. So let's look at this 8 kilometers per second. That means that 4 kilometers per second is not quite fast enough. So after you launch from your mountain, gravity is going to take over, and as you begin to circle the Earth, it'll just get pulled right into Earth. 6 kilometers per second is getting there, but still not quite enough. You make it a little bit further around Earth before gravity pulls you in, but again, your rocket just lands on Earth. This is how you can go about launching rockets halfway around the Earth by carefully choosing their velocity. At 8 kilometers per second, it's just right. It's like the Goldilocks velocity. It's not too fast or too slow, it's just right, and you achieve orbit around the Earth. If you exceed that at 10 kilometers per second, that's faster than needed to achieve orbit, and you can see that we actually start to deflect from Earth a little bit before being drawn back. Now, 10 kilometers per second is slightly below what we call escape velocity, which is the velocity needed to escape Earth's gravitational field completely, which is about 11 kilometers per second. Now, you don't need to achieve 11 kilometers per second in order to escape Earth's gravity. You can actually do that with any type of velocity as long as you have a sustained force pushing you away from Earth. These velocities that we're using in these examples here, we're assuming that there's an initial velocity but then no sustained force, and just seeing how far that initial velocity can propel your object before gravity takes over. So at 10 kilometers a second, with no sustained force after the initial moment, your rocket would be overpowering gravity, so it would start to float away, but then because there's no applied force, gravity would be slowing it down, which in this animation is what's happening all the way through here. So it's leaving gravitational field, being slowed down. At this point, gravity finally starts to pull it back in and then draws it all the way back to the surface. So it's important to recognize that in these examples, we're assuming that there's no sustained force applied. Space Shuttle Orbit. Space Shuttle Orbit is an example of LEO, or also called low Earth orbit. It's approximately 200 kilometers in altitude above the surface of the Earth. These space shuttles orbit with a period of approximately 90 minutes at a velocity of 7,800 meters per second. We're going to go through a few different types of orbits here, so I suggest you make a list of these and keep track of them. You should have some kind of distinction in your mind between the different types of orbit. So, Space Shuttle Orbit would be an example of LEO, low Earth orbit. Then we can move on to mid-Earth orbits. These are usually communication satellites, GPS nodes, things like that. These orbits have a half-day orbit, so a 12-hour orbit, about 20,000 kilometers in altitude with a velocity of approximately 3,900 meters per second. We also have what are called elliptical and polar orbits. These are often things like spy satellites, scientific sun-synchronous satellites, and things like that. So an elliptical orbit would just be, as it sounds, something that orbits in an ellipse rather than in a circle. And a polar orbit would be an orbit that passes over or very near both the south and north pole of the Earth. Next up, we have geosynchronous orbits. Here, the altitude is chosen so that the period of orbit, the amount of time it takes to go around the Earth, will be 24 hours, the same as Earth's rotation. The altitude is about 36,000 kilometers, which is approximately um, 6 times the size of Earth's radius, so approximately 6 Earth radii, and the velocity is about 3,000 meters per second. There is a special case of geosynchronous orbit where if we orbit at the equator, we can stay above the same spot on Earth, and this is called a geostationary orbit. So geosynchronous just means that the amount of time is 24 hours, but it might circle the Earth at any place or in any direction. But then a geostationary orbit is a special type of geosynchronous, so it still takes 24 hours, and it's set up in such a way that it matches Earth's rotation so that to somebody standing on Earth, it would look like the satellite never moves because it would always be orbiting Earth right above the same spot. These orbits are very cluttered, and currently we have approximately 600 satellites in orbit in this category. Looking next at rotating space stations and how they might simulate gravity. So the International Space Station does not rotate. This is a picture from Space Odyssey 2001. But the idea is to create a space station that looks like this, that would spin, similar like a bike tire. So based off of this axis in the center, your offices or cubicles or whatever would be in this outer rim. Um, and just like spinning a spinning drum in an amusement park, it would create gravity in space via rotation. Thinking about where would the floor be in this space station? Well, as you spin, you would be pressed to the outside by the centrifugal force. So as you're pressed to the outside, if you think about just being in a regular room right now, you're pressed towards the floor. So in this spinning station, you're pressed towards the outside. So that means this outer rim would all be considered your quote unquote floor. This inner rim would then be the ceiling, and this side that we see here with the windows would be your sidewalls. Where would you still feel weightless? Right in the center, where you don't experience any of that centrifugal force. Note the windows on the face of the wheel, still allowing you to look outside, and also again working with that idea of the outer rim as being the floor, and so then the windows on the side would be your sidewalls. Now, we don't actually have any of these spinning space stations currently. No one, including NASA or anyone, has gone to the work of developing them yet. They're just theoretical ideas at the time. Question: how fast does the ISS, International Space Station, travel as it circles 400 kilometers above the Earth? We can go back to this equation that mv squared over r will have to be equal to gm1 m2 over r squared. We have the mass of the Earth listed as well as the radius of the Earth. We can reduce our equation again to v squared equals gm over r by reducing both sides by m and r. We can then square root each side to find that velocity will again be equal to square root gm over r. Plugging in then the gravitational constant as well as the mass and the radius, we end up with this equation, and calculating it out, we get that the velocity will be 7,670 meters per second, or approximately 28,000 kilometers per hour. How long does it take for the satellite to orbit the Earth? Time would be distance divided by velocity. Now the distance, since we're traveling in a circle, would be the circumference of that circle, which is 2 pi r. So we can say that the time to orbit the Earth will be 2 pi r over the velocity. We can replace r with the radius of travel. Now this radius of travel would be the radius of the Earth added to that, the distance that the satellite is above the Earth. That's going to give us the total radius of this orbit, and then divided by the velocity, which we know is 7,670. Dividing this out, we will find that the time is 5,554 seconds, or approximately 93 minutes. For some practice work, we're going to look at page 303, numbers 1, 4 to 7, and 9.